Okay, it's recording. So I share my screen. I give it a few minutes so that everybody can see my screen. So for today, we shall look at the second case for obtaining the confidence interval. And in the second case, we have normal populations. But the variances are unknown. In the second case, we are trying to get the confidence interval for a difference of two means. So in the second case, the populations are normally distributed. But the variances are unknown. Normally distributed, but the variances are known. So I can just write like this: variances are unknown. If the variances are unknown, so far with the statistics that we have been doing, you know that if variances are unknown, most of the time we are required to calculate it, because we need the sample variances in our computations. Now, before we go far, I want to mention something here which we refer to as the rule of thumb. Rule of thumb. I have said that in the second case, we are considering a situation where the populations are normally distributed, but the variances are unknown. Now, the question is this: if the variances are known, is it that the variances are equal? You know, we may not know the values of the variances of the two different populations. We do not know them, but it is possible that the variances for the two different populations are equal or can be assumed to be equal. That is one case. The other case is that those variances for the two different populations, they may not be equal. So it is possible that the variances are equal. It is also possible that the variances are not equal. Now, what is this rule of thumb? The rule of thumb is used to test for equal population standard deviations. The rule of thumb is used to test for equal population standard deviations. That is if the larger standard deviation. Why am I talking about standard deviation? I'm talking about standard deviation because the population variances are not known. And if the population variances are not known, then we have to calculate sample variance. And from sample variance, we get the sample standard deviation. Now, the rule of thumb, as I said, is for testing equal population standard deviations. That is, if the larger standard deviation over the smaller standard deviation, if the larger standard deviation over the smaller standard deviation, if this ratio is less than 2, if that ratio is less than 2, then we assume equal population variances. if the ratio of larger standard deviation to smaller standard deviation, where do we get these standard deviations from? We calculate them from the given data. Because the population variances are unknown, they are not given. So we have to calculate sample variances. When we get the square roots of the sample variances, then we get the sample standard deviations. Now we are considering two populations. Once we calculate the sample standard, the sample variances, and we get a square root which gives us the sample standard deviation, then we shall take the larger standard deviation and we divide it by the smaller standard deviation. And if that ratio is less than 2, then the population variances are assumed to be equal. Please write that. If this ratio, which we are calling the rule of thumb, is less than 2, then the population variances are assumed to be equal. Now, you see, if the population variances are assumed to be equal, what are we saying? We are saying that sigma 1 squared is assumed to be equal to sigma 2 squared, because you are considering only two populations. So if we make a conclusion that sigma 1 squared is equal to sigma 2 squared, that is, the population variances are equal, and yet these population variances were not equal, then we need to estimate sigma squared. Now, obviously, being engineers, you are mathematicians. So if sigma 1 squared is equal to sigma 2 squared, then it is correct for us to say that it can be sigma 1 squared, which is equal to sigma 2 squared, can just be equal to sigma squared. If the variances are equal, then the variance of the first population, which is equal to the variance of the second population, we can just equate that to sigma squared, because those two variances are equal. Now, how do we estimate sigma squared? So we need to estimate that, and we usually estimate that by getting the pooled sample variance. We compute the pooled sample variance. This is a small s, please. It is a small s. It is not capital S. Capital S is something else in statistics. So I'm just talking about the pooled sample variance. To get this variance, which we are saying, which is equal to sigma 2 squared, which is equal to sigma 1 squared, we need to calculate it from the sample data. And so what we get is the pooled sample variance, whose formula is given by square root n1 minus s1 squared, n1 minus s1 squared, I made a mistake somewhere here, sorry, n1 minus 1, and it is not ni anyway. Why am I thinking in terms of ni? It is n1 as in the sample from population, the sample from population 1, n1 minus 1, s1 squared, plus n2 minus 1, n2 minus 1, s2 squared, over the degrees of freedom, which I want to draw a line here. Okay, n1 plus n2 minus 2. So this is the formula that gives us the pooled sample variance. So of course, if we get SP, this is known as the pooled sample standard deviation. SP, of course, SP is the square root of SP squared. So SP is the pooled sample standard deviation. Now, why are we calculating SP squared? Because population variances are assumed to be equal. And if that is the case, then our confidence interval will be given by x bar 1 minus x bar 2 plus or minus T alpha over 2 So why T alpha over 2? Because we are calculating pooled sample variance. Whenever we calculate the variance, we use the T table, square root SP squared over N1 plus SP squared over N2. So this is the formula for the confidence interval. So we can look at an example, but before we look at the example, you need to note something. Note that this T alpha over 2, that T alpha over 2 has how many degrees of freedom? N1 plus N2 minus 2 degrees of freedom. It has N1 plus N2 minus 2 degrees of freedom. We know that in the T table, we must always know the degrees of freedom. Okay, let's look at an example. Let's look at an example. Two samples from normal populations, with unknown variances, consist of the observations, 4, 7, 8, 7, 9, 4, 7, 8, 7, 9, and the sample from the second population, 5, 4, 8, 6, 7, 8, 6, 7. So these are samples which are drawn from two different populations. The first one is from the first population. The second one is drawn from the second population. So the question is, find the 95% confidence interval for mu1 minus mu2. We need to find the 95% confidence interval. So if we look at our formula, now we are things like x bar 1 and sample variance. We are experts at getting this Okay, we have been asked to find the 95% confidence interval for mu1 minus mu2. The first thing that should come to our mind is to check whether population variances should be assumed to be equal or whether they should not be equal. And we know that the rule of thumb helps us to determine whether the population variances should be assumed to be equal. So this is what we must do first. We must first check for equality of population variances. That means that we need to calculate the standard deviations for the two different the standard deviations drawn from some birds are competing with me, sorry. So we need to calculate the standard deviations for the two samples. So considering sample number 1, first of all, x bar 1 is equal to 7. And you know now, you guys should be professionals of getting sample variances. So considering the first sample, S1 squared will be 3.5. For the second sample, x bar 2 is equal to 6. And then S2 squared is equal to 2.5. So now that we know the two sample variances, now we need to check what the ratio of the larger standard deviation to the smaller standard deviation gives us. Now, the larger standard deviation is square root 3.5, because remember that is 3.5 is sample variance. We need the sample standard deviation. So square root of 3.5 over square root of 2.5. This will give us 1.8, and we can see obviously that 1.8 is less than 2. It is less than 2. And because it is less than 2, then we can assume that the population variances are equal. We can assume that the population variances are equal. And if that is the case, then we need to estimate sigma squared. We need to estimate sigma squared by calculating the pooled sample variance. So by calculating the pooled sample variance. So our pooled sample variance, let me just substitute the values. Okay, I can see there is a contradiction there, and I cannot see that anybody raised it up. Sorry. Maybe, here, okay. I can see a mistake there. Let me call this equation 1, the one for the pooled sample variance. So I have written here SP squared. So if I wrote SP squared, then there should not have been a square root sign. If I put a square root sign, then it means that what I have here is pooled sample standard deviation. Please correct that, and sorry for that. And so even on the sigma squared, it should just be sigma. Sorry for that, sorry. It should just be sigma. It looks like my network is giving me a danger signal. I hope it will not throw me out. Okay, so I'm just saying that sigma, which is a population standard deviation is estimated by pooled sample standard deviation. It is estimated by pooled sample standard deviation, which is given by square root of the quantity in equation 1. So let us so we can just calculate SP. We can calculate SP, and if we calculate pooled sample variance, which has the square sign, then the quantity in the bracket will not arise. And actually, if we look at equation 2, what we need is the pooled sample variance. So let us just calculate SP squared. So let me substitute in SP squared, because sometimes for those who may have a network problem, I cannot just give the answer. So the two samples, what are their sizes? N1 is 5, N2 is also 5. That is the sizes of the samples, sample sizes, because we need to know what N1 is and what N2 is. So substituting N1 minus 1, that is just 5 minus 1, multiplied by S1 squared. S1 squared, that is multiplied by 3.5. Plus N2 minus 1, which is also 5 minus 1. 5 minus 1 multiplied by S2 squared. And what is S2 squared? 2.5. All over N1 plus N2 minus 2. So that is going to be 5 plus 5, 5 plus 5 minus 2. And if we calculate this, we find that SP squared is none other than 3. It is none other than 3. Now, so x bar 1, x bar 2, we have SP squared, we have N1 and N2 we don't know the value of T alpha over 2. We don't know the value of T alpha over 2. Now, our level of significance is 95%. Our level of significance is 95%. I will not get tired of drawing the distribution, T distribution, 0.95 in the middle region. If that is the case, then we are dividing 0.05 by 2. If we divide 0.05 by 2, then we have 0.025 on the right side, and also on the left side, the area on the left should also be 0.025. Just excuse me. Sorry for that interruption. There was something which was a little bit urgent. So let us just continue. Okay, Lucy Nyawira is talking to me, and 1 minus 0.95 divided by 2. You are very correct. I'm getting SP raised to 2. Oh, he's getting pool sample variance as 9.25. No. That's not correct. What is this? Around 13 plus around 10, 20 something divided by 8 is around 3. Please, Njage, please just calculate again. Lucy Nyawira, your comment is right. It is 1 minus 0.95 divided by 2. Let me just look at, Njage, please calculate again. Okay. 0.025 where from? Oh, Rashid was asking. Yeah. And I think that is why Lucy answered. Lucy answered, and she answered correctly. And I can still explain that. I will still explain that. Yeah. Okay, so even Dahir is assisting Njage. Dahir is assisting Njage by explaining why it is not 9.25. So let us go back to my whiteboard. So why 0.025? The middle area is 0.95. So, you know, for as I said, when we were learning how to read the T tables, we talked about T alpha, and we said that T alpha represents the area to the right. That is why, first of all, we know that under the curve, whether it is normal distribution or T distribution, the area under the curve is 1. So if the middle area is 0.95, then what is 1 minus 0.95? It is equal to 0.05. It is equal to 0.05. And why are we getting 1 minus 0.95? Because we want to know the area to the right, and you also want to know the area to the left. The area to the right is going to help us to determine the T alpha value. So 1 minus 0.95 equals 0.05. So when we get 0.05, we know it represents the sum of the area to the left and the small area to the right. So we need to divide that by 2. Dividing that by 2, that's how we get, dividing it by 2 areas, we get 0.025 to the right. So, so then we know that we shall look for T 0.025. We shall look for T 0.025 and the degrees of freedom. So what you realize, okay, there is a comment, but before I look at it, let me just finish this sentence because I'll forget. Now, what you realize that whenever we are doing our calculations, before we usually go to the table, whether it is normal, T, F, or whatever, first of all, we usually do some calculations here so that we know what we are going to look for once we get to the table. So like now you can see we are looking for the level of significance. We are using the level of significance to get 0.025, and also we need to know the degrees of freedom, which are 8, before we go to the table. So we need to do this, our calculation here. We have to know in our mind's eye how the distribution looks like to give us the areas to the left and right. And then we need to know what we shall go to look for in the table. There is no need of going to the table without knowing what we are looking for. Now let me take the question first before we continue. Oh, great. Njage has got it. That is fine. It's good when students understand. So I hope we are still together as we are saying T 0.025 with 8 degrees of freedom. And as usual, this is the class rep. Okay, class rep for FCE. What is the problem? You can't hear me?
You are breaking. I couldn't hear you.
Okay, where do you want me to repeat from?
You just started talking about the alpha over 2 with the degree of freedom 8.
So I need to talk about the part on the curve, yeah? I can start there again.
Okay.
Yeah, okay, it's fine. It's fine. Okay, so the class rep has told me to repeat a little bit on this part where my voice seemed to have been breaking. I think maybe in the evenings, Wi-Fi, everything gets tired. Maybe by evening, Wi-Fi is tired. Okay, so I'll repeat again. Our level of significance was 95%, So if the level of significance is 95%, then we are saying that the middle area should be 0.95, And what does that imply? If we subtract 0.95 from 1, we get 0.05. Now, this 0.05 it is a sum of the small area to the right and the small area to the left. Because remember, this 0.95 is a middle area. If it is a middle area, what is on the right and what is on the left should be equal. So now that 0.05 we divide by 2. If we divide by 2, then the area on the extreme right is 0.025 and the area on the extreme left is also 0.025. Why are we looking for this 0.025? It is because, if you remember, when I was teaching you how to read the T tables, the T, chi, and F, T alpha refers to alpha area to the right. So at this point where I've written T alpha, it should actually be T 0.025. Why? Because the area to the right from this place where I have written T alpha, the area to the right is 0.025. So when we go to the tables, we should look under T 0.025. Then we need to ask ourselves, how many degrees of freedom? Because we know the T tables has, we can't read anything unless we know the degrees of freedom. Now, the degrees of freedom are N1 plus N2 minus 2. So the degrees of freedom are 5 plus 5 minus 2. 5 plus 5 minus 2. So what is 5 plus 5 minus 2? It is 10 minus 2. So the degrees of freedom are 8. The degrees of freedom are 8. So when we go to the tables, we will look for the value which corresponds to T 0.025 with 8 degrees of freedom. And as I always do, I always try to show you that I also know how to read my tables. So I want to open my tables, and I don't want to stop sharing the screen because I don't want the previous problem to come up. So what are we looking for? Yeah, the T tables. I can't see my T table. Yeah, there it is. It's opening. T 0.025 with 8 degrees of freedom. T, okay. So now on the left side, I can see 8. The first number I see is 1.397. At the top there, it is T 0.10. Moving towards the right, I can see at the top T0.05, but we are looking for T0.025. Moving more to the right, I see at the intersection of 8 degrees of freedom and T0.025, I see 2.306. 2.306. We go back to, okay, so on the whiteboard, the T value is 2.306. Okay, now we can get our confidence interval. Now we substitute. We substitute in equation 2. So x bar 1 is 7 minus x bar 2 is 6 plus or minus 2.306, 2.306, and then multiplied by square root of, what is SP squared? It is 3. That is 3 over 5, because N1 is 5, plus 3 over 2, 3, not 3 over 2, 3 over 5, and 2 is also 5. So the confidence interval will be minus 1.526 minus 1.526 up to 3.526. And remember the way we have been saying that once we get this confidence interval, then we should state that we can be 5% confident that the difference between the two means lies between minus 1.526 and 3.526. So this is how we compute a confidence interval when the variances are unknown, but they are assumed to be equal. Why are they assumed to be equal? Because the ratio of the larger standard deviation to the smaller standard deviation is less than 2. Because that ratio is less than 2. So if there is if there are no queries or comments, then I will continue. And in the next part, that is the part where I usually give the formula in the exam. I remember one of you had asked, because I think remembering equation 1 is not tricky. It's not tricky. Okay, there is a comment. Let me look at that first. Is T alpha equal to T alpha over 2? No. And I want to answer that for the general case. I'm being asked whether T alpha is equal to T alpha over 2. This is not true. It is not true. Why? Because when we write T alpha, then we are saying that the area to the right, the area to the right is alpha. If we say T alpha, so it means that this area here is the one which is alpha. If we say T alpha over 2, then we are saying that the area to the right is that area there is alpha over 2. So there's a difference between talking about T alpha and T alpha over 2. And this person who has asked this question, you see, when we look at T alpha and we look at T alpha over 2, obviously, alpha, this diagram which I have drawn for the first one, we have only one area to the right, which is alpha. But when you talk about alpha over 2, there is an area to the right, which is alpha over 2, and there's another area to the left, which is alpha over 2. Now, this student who has asked this question, I don't know whether you have already gone ahead of us and you're looking at significance tests. Because if you have looked at that, then that could be causing that is what is making you to ask the question. Because when we shall do significance tests after, maybe in the next, after the next subtopic, maybe it's after a topic and then another one. And in the significance tests, we have right-tailed test, where now we shall be talking about alpha, the area being alpha, and there is nothing, and then there is just the acceptance region on the left. And if we have a two-tailed test, then we talk about alpha over 2 area on the right, alpha over 2 area to the left. So the first diagram, where the student has asked about T alpha only, it applies when we're talking about significance tests. Right now, what we are looking at are just confidence intervals. So please, for now, don't get confused in case you have been reading some textbooks and you found some place where they're just talking about T alpha. And here I am talking about alpha over 2. The T alpha over 2 is for confidence interval. But T alpha, we will even do examples about it concerning significance tests, and this one is a right-tailed test. Yes, another comment. Okay, Perez is asking, in the formula, it says we do T alpha over 2. Why are we putting in 2.306 directly? Okay, those questions are good because it gives me an opportunity to explain and clarify. So she's asking, why does the formula say T alpha over 2 and we are putting in we are substituting with 2.306? Okay, I think I can explain this. Maybe because I wrote this to alpha here, T alpha, people are getting confused because of that. What I should have written, this one here, I should have written T 0.05, and the space is so small, T 0.05 divided by 2. Sometimes when we are teaching, we make so many assumptions. Because as we've been working on this many times, sometimes maybe we don't say some things which can make it clearer for the student. Let me make this much more clearer, and I try to explain again. Now, okay, so we have our middle area, which is 0.95. So 1 minus 0.95 is 0.05. This 0.05 is the one which is actually equal to alpha. 0.05 is alpha. Now, 0.05 divided by 2 is alpha over 2. You can see there in equation 2. There is T alpha over 2. So, what I should put on the critical line, which divides the middle area with 0.025, here I should have written T 0.05 divided by 2. And maybe when I wrote T alpha there, and I wrote T 0.05, maybe that is why one of our friends was wondering whether T alpha is equal to T alpha over 2. I don't know whether I'm clearer now. This is T 0.05 divided by 2, which is the one which is equal to T 0.025. Where do we get 0.025 from? It is 0.05 divided by 2. Let me check on the comment again. The formula should read T alpha over 2, not T. Yeah, the first statement is correct, Lawrence. What we should have, if I could write in red at the top left, is T. It is T alpha over 2. It is alpha which is being divided by 2, just as I wrote in equation 2. If equation 2 was not very clear, in case someone thought it was T multiplied by alpha divided by 2, equation 2 should be T. Alpha is the one which is being divided by 2. And in our question, when alpha is divided by 2, it becomes 0.025. There is a comment. Let me look at it. Okay, so our friends want alpha over 2 to be in brackets. If it will make it clearer for you, then I'm happy with that, so that students don't get confused. So this alpha over 2, if we put it in brackets, it means I'm also saying that here we have 0.05 divided by 2. And that gives us T 0.025, and then 8 degrees of freedom. So from the tables, it was 2.306. So now, this 2. Okay, I remember one of the students asked why 2.306 was replacing something. Yes, this 2.306 replaces the whole of T alpha over 2. We went to the table and we looked for T 0.0, we looked for T 0.025, and we found with 8 degrees of freedom, and we found it to be 2.306, and that is why it replaces the box which I have put in equation 2. If there are more queries, just ask. If there are more queries, just ask, because when we go to significance tests, we shall still revisit this. We shall revisit. Okay. Thank you for the questions. Now, we have looked at the second case when we have normal populations and the variances are unknown, but they are assumed to be equal. Why? Because the ratio of larger standard deviation to smaller standard deviation is less than 2. Now we go to the third case. And for the third case, I'm sure one of your friends will be very happy, because for the third case, I usually give the formula in the exam. For the third case, Oops, that's red. So for the third case, we consider populations which are normally distributed, but standard deviations are not assumed to be equal. The populations are normally distributed, but standard deviations are not assumed to be equal. So now we want to look at that case. We want to look at that case. So how do we know that standard deviations should not be assumed to be equal? It happens when the rule of thumb tells us that the standard deviation of the larger one to the standard deviation of the smaller one, the larger standard deviation divided by the smaller standard deviation is greater than 2. If this happens, then we know that the population variances should not be assumed to be equal. If that happens, then the population variances should not be assumed to be equal. So if the population variances are not assumed to be equal, then what is the confidence interval given by? The confidence interval will be given by x bar 1 minus x bar 2 plus or minus t alpha over 2. I will put it in brackets. And then, you know, the variances are not equal. They are not equal. So square root s1 squared over n1 plus s2 squared over n2. And now, when the variances are not assumed to be equal, this T alpha over 2 has delta degrees of freedom. It has delta degrees of freedom, which should be rounded down. Now, delta degrees of freedom is computed using the formula that I have shown on the slide. I usually give this formula in the exam because it's rather confusing. So you see delta is equal to, open the bracket, s1 squared over n1 plus s2 squared over n2, close the bracket, squared, divide by s1 squared over n1 in brackets squared divided by n1 minus 1 plus s2 squared over n2, everything in brackets squared, n2 minus 1. So this is how we calculate delta. Let me just give you a minute so that you copy that. This is how we calculate delta. And once we've calculated delta like that, once we calculate we round the figure that we get, we round it down. We round the figure that we shall get. When we compute delta, we round that figure down. So that is the formula that we use when calculating the degrees of freedom, which are represented by delta. And once we calculate those, we obtain the degrees, then we round it down. So now we consider data set 5, which I had given you. I'm also looking for mine. Data set 5. In our example, in our next example, we want to see how to calculate the confidence interval when the variances are not assumed to be equal. So our example is data set 5, where we have the first sample. We have two samples, of course. In sample 1, X bar 1 is 394.6, S1 84.7, and 1 is 14. And in the second sample, X bar 2 is 468.3, S2 is 38.2, and N2 is equal to 6. So there, we are lucky we've been given S1 and S2. So we really don't have to calculate the sample standard deviations. They are already given. So if they are already given, remember what we need to do first is to check the rule of thumb. We can see that S1 is greater than S2. So we divide S1 by S2 to check for equality of population variances. So we shall divide 84.7 divided by 38.2. And this gives us 2.217. And obviously 2.217 is greater than 2. Since it is greater than 2, then we know that the population variances should not be assumed to be equal. They should not be assumed to be equal. So now we have X bar 1 is already given, X bar 2 is already given, S1 squared is given because we have S1 and S2. We know that all we need to do is to square them when we shall be substituting in the formula. But now we need to know what we are going to look for in the tables. And that reminds me, we are supposed to determine the 99% confidence interval. In that example, we are supposed to look for 99% confidence interval. 99%. So as usual, the diagram, it is t-table. So we know how the t-distribution behaves. It looks like the standard normal. Now the middle area is 0.9. What is 1 minus 0.99? 1 minus 0.99. This is 0.01, if I am not wrong, 0.01. And now we need to divide 0.01 by 2. If I am correct, 0.01 divided by 2, because the small area to the left, the area, both of them sum up to 0.01. So what I need here is t, let me put it in brackets, 0.01 divided by 2. Divide by 2. So what is that? We shall look for t 0.05. But remember, we also need the degrees of freedom. The degrees of freedom are given by delta. So we need to calculate delta. Delta degrees of freedom. How do we do that? Do you mean that I had closed it? It looks like I had closed the... So for delta, we have there S1 squared. No, I don't want to... Where is the most recent? This PC. Recent. Where is delta? Yeah, there. So we need to substitute there. S1 squared, we shall put what? 84.7 squared over N1. N1 is 14. N1 is 14. What is S2 squared? 38.2 squared over N2. N2 is 6. And then we need to square all that. Divide by 84.7 squared divided by 14 quantity squared over N1 minus 1. This will be 13 plus S2 squared, 38.2 squared, divided by 6 quantity squared, and then N2 minus 1 will be 6 minus 1, which is 5. And if we do that, we shall find that delta should be equal to 17.83. 17.83. And we need to round this down. It should be rounded down. So rounding it down, it comes to 17. So when we go to the tables, we will look for T0.005 with 17 degrees of freedom. When we go to our T tables, I don't know whether I had closed mine. No. So let's look for T0.005 with 17 degrees of freedom. Starting from the left, if we go up to the extreme right, because where we have the extreme right, we have T0.005, then we can see 2.898. 2.898. So our answer will be 2.898. 8. And so in our formula, we shall replace T alpha over 2, all of it, we shall replace it with 2.898. So what is the confidence interval? Then the confidence interval will be given by x1 394.6 minus 468.3 as per the data set given, plus or minus, plus or minus 2.898, and then square root 84.7 squared over N1 is 14 plus S2 squared 38.2 squared over 6. And when we calculate this, we find that our confidence interval will be from minus 153.4 up to 6. And so we can say that we can be 99% confident. We can be 99% confident that the difference in means lies between minus 153.4 and 6. Minus 153.4 and 6. Minus 153.4 and 6. Okay, there are no queries, so we can continue just a little bit before 6 p.m. So we go to the next part, confidence interval. So now we are through with a difference of means. Now remember, for the difference of means, there are 3 different cases. Now let's look at confidence interval for population variance. Confidence interval for population variance, sigma squared. Confidence interval for population variance, sigma squared. Now, before we look at the formula for the confidence interval, let us remind ourselves of something that we have discussed before. We said that the curve was right skewed. The chi-square curve is right skewed. You know, for this one, we use the chi-square distribution. We use the chi-square distribution. And we had said that the chi curve is right skewed. It is right skewed. And remember that when we talked about chi alpha with n-1 degrees of freedom, sorry, so their sign. Remember we said that the alpha refers to the area to the right. That alpha refers to the area to the right. So if the middle area is 1 minus alpha, then obviously this one here, sorry for using here, the area, the small area to the right is alpha over 2, and the small area to the left is also alpha over 2. The middle area is 1 minus alpha. Now, when we read when we want to read the values from the chi table, if we want to read the critical value that gives us the small area to the right, we shall be talking about chi alpha over 2, because alpha over 2 is the area to the right. For us to read that critical value, it is chi alpha over 2 and particular given degrees of freedom, which are n-1. What I want you to note is this chi alpha over 2, the one in the bracket. Now, when we want to read the critical value, which gives us the area to the left, which gives us that alpha over 2 area to the left, what are we going to read from the chi-square tables? What are we going to read from the chi-square table? We shall read chi. Remember, we are reading the area to the right. The area to the right. When we want to get this critical value, which gives us the area, the small area to the left, that area to the left is alpha over 2. So what area meaning on the right? The area that is to the right is 1 minus alpha over 2. And I need to put all that in brackets. With particular given n-1 degrees of freedom. Again, what I want you to note is this value in the bracket, 1 minus alpha over 2. So, you need to identify alpha over 2 and 1 minus alpha over 2. You need to know the numerical values before you go to the tables. So, with that understanding, then let me give you the confidence interval for that, for population variance. Confidence interval. So it's opening. So this is the confidence interval for population variance. N minus 1, S squared. S squared is the sample variance, divided by chi alpha over 2 with n minus 1 degrees of freedom. That is the lower value of the confidence interval. What about the upper value of the confidence interval? N minus 1 S squared over chi 1 minus alpha over 2 with degrees of freedom n minus 1. Let me give you a minute or two to copy that. So let's look at an example. Consider data set 6. Consider data set 6 which has sample size 12. Data set 6 has sample size 12. We want to find 95% confidence interval for the variance of the data sets. We want to find 95% confidence interval for the variance of the data set. (95% confidence interval for the variance of the data set. So you can see obviously that in the formula, okay, if the sample is size 12, then n minus 1 is just 11. We need to calculate sample sample variance, because we need S squared. We need to calculate sample variance. And then we need to determine chi alpha over 2 with 11 degrees of freedom and chi 1 minus alpha over 2 with 11 degrees of freedom. First and foremost, we just calculate sample variance. Sample variance, which is given by, you will find it to be 0.0022 sample variance. And now n minus 1 is not a problem. We know it is just 11. We need to determine, we need to go to the chi tables and get this, and we get the values that you're going to substitute in the formulae for confidence interval. So our question requires us to determine a 95% confidence interval level. 95%, as in the middle area will be 0.95. So what are the two? So 1 minus 0.95 is 0.05. 0.05, and this 0.05 is alpha. So what is alpha over 2? Alpha over 2 there, 0.025, because we divide 0. So the extreme small areas will be 0.025. So it means that the critical value separating the middle area from the right area, this is going to be chi 0.025 with 11 degrees of freedom, because n minus 1 is 12 minus 1. It is chi 0.025 with 11 degrees of freedom. Why 0.025? Because the area to the right is 0.025. I need to open my table. Chi-square distribution. Expand it a bit. We are looking for 11 degrees of freedom. 11 degrees of freedom on the left, and 0.025. 0.025 is in the column, second last column. So over there I can see 21.92. 11 intersecting with 0.025, we see 21.92. 21.92. Now, to determine the value, the critical value separating the small area to the left, this one is going to be chi. The area to the right is 1 minus 0.025. Let me write that for clarity. For clarity, it is 1 minus 0.025. Which 0.025 am I from 1? It is the one for the area, the small area on the left, because I want to find, because we need the area to the right. So it's 1 minus 0.025, and that will give us chi. It gives us chi 0.975 with how many degrees of freedom? 11. So going to the table, 11 degrees of freedom, chi 0.975. I can see 2.6, 3.05, 3.8, 2, chi 0.975 with 11 degrees of freedom, 3.82, 3.82. So this is equal to 3.82. 3.82. And so what is the confidence interval. The confidence interval will be given by n minus 1 is 11 multiplied by s squared 0.00 divided by 21.92, comma 11.0022 divided by 3.82, and our answer will be 0.001104 up to, I don't have the other answer. Let me calculate mine, and you also calculate yours. We see you calculate yours, you put on the chart. I confirm with mine. Then my answer is, okay, let me check whether your answer is the same as mine. .00. Hey, you guys are fast. I can see also Majestic, Samuel Kamau, Gashiri, Justin, Simba, Stephanie. It is 0.00633, yeah. 0.00633. Yes, Lawrence, 0.00633. 0.00633. So we can be 95% confident. We can be 95% confident that the variance of the data set is somewhere between 0.001104 and 0.00633 and 0.00633. So this is how we handle the case where what is happening? Where we're looking for confidence interval for population variance. Where we're looking for confidence interval for